wave number is defined as 1 over lambda. And the typical unit that we use for wave number is reciprocal centimeter. So it's centimeters to the negative 1. And the way you read that, say reciprocal centimeters. And so if your photon energy is equal to h nu, okay, and if you recall, h nu is c over lambda, right? Then you can say that your photon energy is hc times 1 over lambda. So 1 over lambda is your wave number. Now, usually this is represented by the symbol nu with a tilde on top. Okay, so this thing right here, that the squiggly line on top of the symbol for nu is a tilde. On your keyboard, that would be, that's the key to the left of the number 1 at the top of your keyboard, but you have to press the shift key. Okay, so nu tilde, that's what you would call a symbol, is a symbol for wave number. So that's 1 over lambda. And so your photon energy then would just be equal to hc times nu tilde. Just make sure, though, when you plug in your numbers that you do have consistent units. Okay? So reciprocal centimeter is commonly used, in fact, by spectroscopists as a unit for energy. Why is that? Well, the energy of the photon, you can see, is equal to some constant times the wave number. So it's proportional, directly proportional to the energy. So since in spectroscopy we're primarily dealing with light, energy of light, since wave numbers directly proportional to energy, it's used as a unit of energy. In fact, you can use frequency as a unit of energy. But reciprocal centimeters is such a very nice number. Those numbers, the reciprocal centimeter values we deal with when dealing with light typically tend to be nice, easy numbers to deal with. Okay, as you can see in just a short while, that it's commonly used as a unit for energy. Okay, so how many joules would actually correspond to one wave number? So the energy for a photon that has a wave number of 1 would be what? H is how much? Okay, 6.626 times 10 to the negative 34 joules second. Speed of light is 2.998 times 10 to the 8 meters per second. And 1 reciprocal centimeter would be 1. And reciprocal centimeter, we have to put it in meters. What's a meter? I'm going to put 10 to the negative 2 meters, right? Centimeter means 10 to the negative 2 meters. So 10 to the negative 2 meters, but I have to take the reciprocal of that. So raised to the power negative 1. Okay, so that's equal to how much? 6.626 times 10 to the negative 34. Oops. Okay. 6.626 times 10 to the negative 34 times 2.998 times 10 to the 8th, okay, times, what is 10 to the negative 2 raised to the negative 1? That's 10 to the positive 2, right? So that's 100, so times 100. That's that, and scientific notation, scientific notation is 1.99 times 10 to the negative 23. So that's about 2 times 10 to the negative 23. That's in joules. Okay? So that is the conversion factor for reciprocal centimeters and joules. So you say 1 reciprocal centimeter is equal to 1.99 times 10 to the negative 23rd joules. So you can use that as a unit of energy, even if you are not referring to a photon, okay? But that would be the energy of a photon if the particular photon is for light that has wave number of 1 reciprocal centimeter. Okay. So typical wave number ranges, as you can see here, is very nice. Yes. Okay. You entered 10 to 10 squared in your calculator. Chances are you put 10 EE2. Mm-hmm. 10 EE2 is actually 10 times 10 to the 2, which is 10 to the third. Common mistake on your calculator. So enter 1 EE2. That way, and so you'll end up with just 20. All right, so typical wave number ranges, microwaves would be 1 to 100 reciprocal centimeters. So these are boundaries that are very easy to remember. Infrared would be 100 to about 12,500 reciprocal centimeters. If you remember your organic chemistry, when you did infrared spectroscopy in your organic chemistry, okay, the instrument that you use to take IR spectrum, okay, monitors absorptions in the 200 to 4,000 reciprocal centimeter range. Okay, you may have used the term frequency, okay, for wave numbers in organic chemistry, and it's understandable because frequency, what's frequency? C over lambda, right? And that is just C times nu tilde. So you can see that frequency is directly proportional to wave number. So frequency and wave number, the words tend to be interchangeably used because a higher wave number would mean a higher frequency. Okay? So the infrared spectrometer that you use in organic chemistry is is the range of frequencies you use there is said to be in the mid-infrared. It's right in the middle of this entire infrared range that goes from 100 to 12,500. Okay? Now, visible range, you're already familiar with that. You know that's somewhere between 400 and 800 nanometers. In fact, okay, this is just what? That is the 400 nanometers in weight. That corresponds to lambda of 400 nanometers, 25,000 reciprocal centimeters. And 12,500 reciprocal centimeters is 800 nanometers. Okay, so you can see your infrared starts off at around 800 nanometers and then goes to longer wavelengths. Okay, so you can see those are very easy numbers to remember. And then beyond the violet, okay, you have ultraviolet, so 2,500 nanometers, 2,500 reciprocal centimeters. That's for 400 nanometers and beyond. 100 reciprocal centimeters, you should be able to easily show that corresponds to a wavelength of about 100 nanometers. Okay, so those are really nice boundaries between the typical spectral ranges we deal with. Okay, so like I said, since frequency and wave number are directly proportional, then the terms frequency and wave number tend to be used interchangeably. Because when you say higher frequency, it means higher wave number.